So let me start by thanking Brian and the organizers for the invitation. Very nice workshop. Um, Wenbin Liu already uh, mentioned this and talked about this thing in his talk, that the uh, induced Compton forces provide a fairly stringent limit on the location of the source. It can be either within few tens or few hundreds of kilometers of a compact object or far away. So small distances where the magnetic field is very strong, the induced Compton scattering is suppressed by a very large factor, or at a very large distances greater than about 10 to the 13 centimeter, where the IC acceleration and the forces are not so important. I think this one doesn't work. I'll just Wenman also showed this particular graph, and that is the only point here that I would like to mention is the following. In principle, sure, one can have the FRB at large distances, but that requires the energy to be very high. And this is the parameter space showing the distance of the shock front from the compact object and the luminosity requirement. So it's a very high energy requirement. So this is the problem, in our opinion, certainly, for shock scenario and at distances greater than what you see here. So what I'm going to do for the remainder of the time that I have got, the talk is really going to be looking at a model where the FRB radiation is produced close in the magnetosphere of a magnetar, okay, within distances of few tens, maybe 100 neutron star radii. So the model is this, that you have a Alfvén wave. Well, some magnetic disturbance could be Alfvén wave that is launched at a frequency of a few tens of kilohertz. And from the surface of the neutron star, this is something that was considered 3 decades ago by Blaise, Blanford, Goldreich, and Maddow, but in a very different context, and that was to explain GRBs in our galaxy. This predates, their idea predates GRBs being established to be cosmological. In any case, the point is that you have some magnetic disturbance that is launched. The luminosity of this disturbance is something on the order of the FRB luminosity. So something on the order of 10 to the 43 arcs per second. The amplitude of this disturbance is large in the absolute terms. 10 to the power 11 Gauss is the delta B, the perturbation of the magnetic field. But the relative, the dimensionless amplitude, which is delta B over the strength of the magnetic field, that's small for a magnetar, 10 to the power minus 4. So it's a very linear perturbation in that sense. The perturbation does grow. This dimensionless perturbation does grow with distance from the object as r3/2. So you see the wave is moving outward, growing in amplitude. This relative amplitude is growing, but for the entire regime of the radius of interest, it remains firmly in the linear regime. Okay, so that's one point. The other point is that in this particular picture, if you zoom in and look at the Alfvén waves, there is a current, there is a plasma current along the original magnetic field line, as long as the wave, the disturbance, the Alfvén wave, k vector is not exactly parallel to the magnetic field. Okay? So there is a non-zero current along the magnetic field direction. That is the current. And that current is being carried by electrons and positrons moving in opposite directions and at a high clip, at some fair fraction of the speed of light, at least few percent, more like 10% of the speed of light. And so these counter-streaming particles are subject to stream instability. And that instability grows on the plasma time scale So which means that it grows on the time scale of nanoseconds or so, and in few tens of nanosecond, you have formation of clumps with delta rho over rho of order unity. Okay? So that's one of the criticism that people had, for very good reasons, for how clumps form in the antenna mechanism for radio pulsars. And so the Alfvén wave, it seems, it provides a way to answer that question. Okay? So that's one component of the model. The other component is the following. The current that is being carried, as I already mentioned, by electrons and positrons, the speed at which they are moving, well, we can calculate that from the current dictated by curl of delta B and divided by the charge, particle charge and their number density. So the V is something that is increasing with distance, with increasing radius. So at some radius, which is RC, the V becomes order C. And that's charge starvation radius, or that's defined as the charge starvation radius, which means that beyond this radius, the charge density, there's just not enough charge density to supply this current for the Alfvén wave, curl of delta B. Okay? So what happens at that stage is that electric field develops. To be precise, it is the time derivative of the electric field. The displacement current now is compensating for the deficit of the plasma current. So you have a electric field that develops, a strong electric field that develops outside of this charge starvation radius. And the direction, a component of this electric field, just like the current density, is along the magnetic field lines. So outside of the charge starvation radius, what we have is a strong electric field and particle acceleration and curvature radiation. And the way it works is this, that Alfvén waves now, going outside of the charge starvation radius, this clumping, plasma clumping has been produced by the instability to stream instability on a short time scale of, as I say, few tenths of maybe nanosecond. The period of the wave or the frequency of these Alfvén wave is tens of kilohertz. So certainly something on the order of the Alfvén wave period is something on the order of tens of microsecond or so, where these things are growing on a time scale much smaller than that. Okay? And then there is an electric field along the magnetic field line. So that accelerates these charge clumps. And these clumps follow the curved magnetic field lines and produce curvature radiation. Right? And the electric field supplies the energy for these particles as they are radiating and they are experiencing this collective radiative reaction force. And that's a little tricky business. See, if the electric field is turned on very quickly, and that very quickly means on a time scale very much smaller than a microsecond, then particles will be accelerated individually in the sense that the radiation reaction force will act on particles individually. They are not going to be in causal contact such that the radiation reaction force is going to be applied on particles as part of a clump. In the former case, when particles are accelerated and the radiation reaction is acting individually on particles, then particles gets accelerated to very high Lorentz factor of order of million or tens of million. And when they are in causal contact and they experience the radiation reaction force collectively, then the Lorentz factor of the clump is limited to something on the order of 1,000. Okay? So it's very, very important that the electric field is turned on. But as I say, that is a natural thing because the Alfvén wave frequency is tens of kilohertz. So the electric field is turning on time scales of many tens of microsecond time scale. That's long enough that particles in the clump are in causal contact and they experience this radiation reaction force collectively. Okay? So So the energetics for this process turns out to be quite efficient as per our calculation. Order unity, which means that order unity fraction of the Alfvén wave luminosity and energy is converted to these coherent radio waves. So that's very different from the previous talks that we have heard, where the efficiency is low-ish, quite low. So the total energy in an outburst for this particular model is not very different from the energy requirement for FRB, which, correcting for the beaming, these things are beamed indeed within an angle of 1/gamma. Gamma is the Lorentz factor of these clumps. So energy is 10 to the 36 arcs or so. And the total energy in the magnetic field is much larger, so this is clearly not a problem producing multiple bursts or even large number of bursts. Right? Some predictions, and they are, so maximum of FRB frequency, that is set by the size of these clumps, which is in turn set by the plasma frequency. Right? So according to this model, we shouldn't see FRBs at frequencies greater than approximately 100 gigahertz or so. So that's the limit set by the plasma length scale. And the density at the Alfvén, for the plasma density at this charge disturbation radius is something that can be calculated with some degree of confidence. So putting it together, seems like that the maximum frequency at which we can see FRB should scale with the luminosity of the FRB to a quarter power. So at least there is this correlation expectation according to this model. Wenbin has already mentioned that the other consequence of this, or prediction of this model, is the maximum FRB luminosity, which is set by simply the swinger limit, the breakdown of vacuum. When the electric field, this is not the electric field of the FRB radiation, this is the electric field that is accelerating these clumps of particles. When that approaches to within about 10% of the swinger limit, then there is a breakdown of vacuum, electron positrons are created, they short out this electric field, no acceleration of clump, well, no FRB radiation. Okay? So that's another prediction. There is a minimum luminosity also, and that is set by the fact that if the Alfvén wave luminosity is small, smaller than a certain number value, then Alfvén waves don't become charge starved. They will become nonlinear before becoming charge starved. Okay? And so that's not likely to, although I'm going to defer to Roger here. I may be misrepresenting, so maybe let's just wait. Roger has some interesting idea for a disturbance. Is it becoming nonlinear and then producing FRB? So let's wait to hear if it becomes nonlinear. So point here is that at some luminosity, when the Alfvén wave luminosity falls below a certain threshold, the wave is likely to become nonlinear before becoming charge starved. And there is a story that we will get to hear shortly. Okay? But in any case, that minimum for this thing is something on the order of 10 to the 39 arcs per second. We are certainly close to it or approaching it. So time will tell. There is a minimum frequency. That's just set by the causality argument. Just simple causality sets the largest wavelength that we should see, or the smallest frequency that we should see, something on the order of 100 megahertz, which is also an interesting number for observers to check. This is something that has been covered. It's not a prediction, it's a post-diction. So Jason, you said you wanted to have post-diction, right? Okay.
I'm in my prediction.
Post-dictions, okay. Anyway, so I put that in, post-diction. He wanted to say, okay, what about post-dictions in an email to me? So here's the post-diction. And I will not say much because there's something nicely covered in Wenbin Liu's talk. So I am repeating here what Wenbin has already said. The natural prediction of this model is 100% linear polarization. It's only the X mode that is produced in the curvature radiation and that is able to escape from the magnetosphere. Okay, so 100% linear polarization. The direction only changes of the polarization angle changes only because, well, in this model, if the magnetic axis is not aligned with the rotation axis. So our interpretation would be that for 121102, which seems to have a swing, polarization angle swing of 20 degrees, that there is an angle between the magnetic axis and the rotation axis that is about 20 degrees. That would be the interpretation according to this model, right? And I'm going to stop. So let's just let me leave the summary slide and let's take questions. So,